Good afternoon, everyone. Sorry for my absence. Now I would like to introduce our survey of face detection algorithm on low-quality images. We are the IFP group from UIUC, and my supervisor is Professor Thomas Huang and Yuqian Zhou, and my partner is Ding Liu. Face detection is a well-explored problem. Many challenges on face detectors, like extreme poses, illumination, low resolution, and small scales are studied in the previous work. However, previous proposed models are mostly trained and tested on good quality images, which are not always the case for practical applications like surveillance systems. In this research, we want to make a survey on current state-of-the-art face detection algorithms and the influence of the algorithm on low-quality images detection. Finally, we will try to provide some suggestions on quality invariant face detection research, which will be done in future work. Face detection has been intensively studied in the past decades because of its wide applications in face analysis. As an important processing step for face recognition, a robust detection algorithm is expected to identify faces under aperture image conditions. Previous work has demonstrated robustness in the face conditions like extreme poses, multiple face scales, and occlusions. However, in the practical surveillance system, the face detector should have the capability of detecting faces in low-quality images with distortions like blur, noise, and low contrast. Therefore, it is necessary to evaluate the performance of the existing face detection algorithm on images with various distortions. Face detecting algorithm can be categorized into traditional methods and deep learning-based method. I will introduce our survey in the following slides. So the first part is about traditional face detectors. Traditional methods can be further categorized into cascade methods, approaches based on the deformable part model, and aggregated channel features. We list some important work in each family. Traditional method is more useful for frontal face detection because of hand design features. It is very fast and can run on video stream in real time, but it cannot handle high variant real cases like extreme poses and illuminations. Here is a brief table of the performance on FDDB database of the traditional face detectors. For the cascade approaches, it is the fattest one among all the traditional methods. If we simply use pixel difference features, the efficiency can reach as much as 416 frames per second. For the aggregated channel features, since it is more like integrating different channels of handcrafted features, usually it will get better performance. Actually, it obtains the best performance among all the traditional methods. The winner of the FDDB comes to the LDCF in 2016. Not surprisingly, the detection speed decreases as the feature number increases. So the traditional methods are fast, but maybe not robust enough on large face and environment variance. As the development of the deep learning algorithm, applying CNN-based model greatly improved the performance. In the following, I will briefly introduce some important deep learning-based methods. So the first class of deep models is Cascade CNN series. It requires an image parameter input to cope with the multi-scale problems. Usually, the main idea of cascade method is to deal with easy case first and difficult ones later. Thus, we first reject some simple negative samples at early stages and then pass the left samples to the next stage. The recent work called ICC-CNN model the rejection process to model the rejection process in the internal layers of CNN. For each level of feature maps, a classifier is trained to reject the easiest samples and then pass the left into the next level. So cascade method is relatively faster than other methods. So face detection is a special case for generic object detection. So many face detector is derived from object detection algorithm. One type of it is from a faster RCNN. It can be regarded as a scale invariant model. Since faster RCNN usually utilizes the feature maps in the last convolutional layer and applies an ROI pooling, Here, RY pooling will output fixed size feature maps from multi-scale receptive field. Therefore, detection windows of all the scales will be processed by a same classifier. So some variant of face detector based on fast CNN also explore on using multi-layer features and aggregate them in the RY pooling layer, like the CMS and the DPIR. The common problem of faster CNN is that it is not good to find tiny faces. The main reason is that they only extract the high-level features and the ROI may have larger receptor field overlap. So another type of face detector is based on SSD. Different from faster RCNN, SSD can be regarded as the scale variant method. Simply to say, it uses different classifier for different levels of feature maps. So the intuition is that multi-scale feature maps will be suitable for detecting multi-scale objects or faces. So the disadvantages of SSD is that it is hard to detect compacted small objects, which is a serious problem for face detection. So one of the reasons of that is it uses a predefined anchors, and some of the faces may not be able to match the anchor. So to solve the original problem of SSD, some of the work will try to adjust the anchor matching strategy. One of the important work is S-FD, and it claims 4 problems of anchor-based approaches for face detection. The basic idea is that the anchors cannot perfectly match the set of faces, and it causes a low recall rate and bad feature extraction process. So the first strategy they used is reassigning the anchor. For each layer, they applied increased the level of strand and anchor scale, and to balance the anchor's density. Another strategy is to compensate the matching number by lowering the threshold like this. So we now compare their performance on FDDB database. So Cascade CNN is the fastest method among all the deep models, and faster RCNN is the slowest approach. SSD-based methods obtain the best performance on FDDB database, and SFD is the winner. It can reach the recall rate about 0.98, which is pretty high, and actually can be applied in some markets, but not just in the lab. So even though the face detector has achieved a high performance on benchmark, its performance on low-quality images is still not clear. We are interested in whether the current designs of detection algorithm will help the robustness on blurry images or other low-quality samples. It is not surprising that those features are not robust enough, but we will expect that the spatial design of multi-scale could help to resist the image quality degradation, especially blur. That is because there are some but not too many blurry tiny faces in the original training data sets. So if we blur the overall images, larger faces will become blurred, and with multi-scale design, the detector may still be able to detect those larger faces. So therefore, we wish to find out the relationships among multi-scale designs, feature extraction, and performance degradation. This is the main difference of the work compared to other investigation work, purely on features of deep networks. So here are some types of image quality degradation, like Gaussian blur, downsampling, noise, etc. So in this research, we consider blur, noise, and brightness as the influence factor. Thus, we process the original datasets first and test the algorithm, like this. So we have different levels of image distortion. Like the blur, we have to set the sigma value to be 2, 4, and 6, and we always cite other kinds of distortions like what I've shown in the figure. So here are 2 questions we consider here. Are the traditional or deep models for face detection robust enough to image distortions? And which model is better for detecting small blurry faces, scale invariant or scale variant? We select 2 traditional methods, the hair lag AdaBoost and Huang SVM, as well as we also select some 2 deep models, FastRCN and SFD. The experiment results for three types of distortions is shown here. So the first row is the ROC curve of SFD under different distortions. To compare different models, we can visualize the decaying rate of record value at the level of distortion increase. For blur, fast RCN drops faster than SFD. That is because fast RCN utilizes the last layer feature map for detection. They are influenced more than the lower layer feature maps by blur input. But SFD utilized all level features to train scale variant detectors, thus it will be more robust. For the noise, all the algorithm cannot achieve good detection if the image is very noisy. And contrast level can be adjusted by normalization, thus the detector is less influenced. Therefore, we can conclude that both traditional and deep models are not robust enough to image distortions, and SFD methods are better for detecting blurry small faces. That results from the multi-level feature usage of the algorithm for multi-scale face detection. It inspires us to develop blur invariant face detector by using all level features by training a scale variant model. That is all for this research, and for any questions, please kindly send email to the following address. We will be more than happy to listen to your suggestions. Thanks again.